entitled Deep Learning for Self-Tuning of Control Systems. Before moving on to the main idea of our research, let us first revisit some of the major challenges in design and implementation of control systems that we seek to address through this research. The first challenge is that of loop delays. Loop delays may arise from control interfaces, from processing time, and from modeling techniques that are used to model complex systems, which may include model order reduction techniques. Such loop delays, they may cause outdated information supplied by measurement channels if the delays are in the measurement channels, and if the delays are in actuation channels, it supplies deferred control actions. It also reduces the performance, and it also complicates the design process because modeling of these loop delays is not done through the usual finite dimensional ordinary differential equations. Rather, infinite dimensional functional differential equations need to be considered. Second challenge is that of non-linearities, which are inherently present in many real-life systems. They also reduce system performance. They also complicate the control system design. They also introduce computational burden on the system processing. Another challenge is that of stochasticity. There are inherent parametric uncertainties in different systems. There may be inaccuracies in modeling and design. So this exposes the system to errors, especially in highly sensitive systems. This also complicates the design. This introduces unknown disturbances, which may cause instability of the system. Another challenge is that of sensitivity. We know that highly sensitive systems like low inertia power systems, microgrids with high renewable energy penetration, hypersonic flight vehicle control, control of power electronic converters, automatic process control, and others, these systems, they are highly sensitive to parametric changes, to changes in control parameters, to changes in the input. So this also results in reduced performance and complicated design of the control system. In the current study, we aim to address these problems through deep learning using estimation and prediction features of deep neural networks. So how we do that? We propose and use a two-dimensional multi-layer deep neural network to achieve adaptive, model-free, and data-based control of highly non-linear systems. We use the deep neural network features of adaptive learning, inference of latent variables, and time series prediction to update the controller parameters on the run in real time. We also compensate for loop delays and system processing time. The proposed technique that we like to call as deep learning based self-tuning algorithm is generic and can be used for online self-tuning of controller parameters in general. However, here, for the purpose of comparison, it's applied on the speed control of brushless DC motor in an electric vehicle using PID controller on the front end. The simulation results demonstrate the superiority of the proposed scheme over other conventional tuning methods. This is the example that we have taken. On the left side, you can see the basic equations of brushless DC motor, equations of phase voltage, back EMF, and torque. On the right hand side, you can see the representation of the system that we have taken. The point to be noted here is that the error signal that is fed to the PID controller, it is the difference between the desired speed R and the actual speed Y. Our aim is to minimize the error. So coming back to the proposed method, as we said, it is a two-dimensional multi-layer deep neural network. The first dimension is that of time dimension, which is based on recurrent neural networks. And we use its prediction feature to compensate for the delays. The second dimension is that of space dimension, which is based on simple feed-forward artificial neural networks, and we exploit the ANN features of estimation, inference of latent variables, and adaptive learning to adaptively change the controller parameters according to the changing conditions in real time. A little bit of detail of what we are exactly doing is that the estimation of space dimension, the ANN-based space dimension, it estimates the nonlinear dynamics between the controller parameters, the three controller parameters, the error signal, speed commands, and the road inclination. Error signal E, speed command R, and road inclination pi. So we assume that error signal E is a function of a highly nonlinear function of R, phi, Kp, Ki, and Kd. So E depends on these five factors. From this, we can get that mathematically manipulating it, the three controller parameters Kp, Ki, and Kd, they are a function of R, phi, and E. The job of the ANN-based space dimension is to estimate this function. For that, we need the training data first. Training data generation, it's completed offline, so we do not need to worry about the processing time. It is completed using genetic algorithm. What we do is, for all possible speed commands in the range of 1 to 100 km/h with an increment of 1, and for all road inclination angles in the range of -45 to +45 degree with an increment of 1 degree, we run the genetic algorithm. It's run 9,100 times, which is the all possible combinations of the speed commands and the inclination angles. So it's run this much of times, while the objective function of the algorithm is to minimize the error signal. So during each attempt of running GA, it minimizes the error signal by changing the three controller parameters for each combination of speed command and road inclination angle. And during each iteration of each attempt of running GA, we record the values of all these six parameters: the road inclination angle, foot pedal speed command, the PID controller parameters generated during each iteration. They are stored as the training data. So then we train the ANN-based dimension where we have the error, and road inclination and speed commands as the inputs, and the outputs are the three controller parameters. So as we said, the assumption is that the controller parameters are a function of E, R, and phi. So if we input any combination of error, speed command, and road inclination, we will get the corresponding Kp, Ki, and Kd. So which may correspond to optimal values, that is error nearly equal to 0, or even non-optimal values where error is not equal to 0. However, the choice of genetic algorithm for generating training data, it is inspired by the fact that most of the training data will be concentrated around the optimal values, which is expected to be the situation that occurs in real life conditions. Finally, how to deploy? While deploying the neural network, the trick is to simply set E equal to 0, the error equal to 0. So effectively, it's giving us Kp, Ki, and Kd for corresponding R and phi, the speed command and the road inclination, which are taken in real time from the system, while the error is kept equal to 0 manually. On the right side, you can see the space dimension. Its back propagation through space is done offline, while as the forward propagation is done online on the run. So the three inputs to the space dimension are the R, phi, and error. The error is manually kept equal to 0, while as the R and phi are fed from the time dimension. The output of this dimension is the Kp, Ki, and Kd corresponding to the predicted R, the predicted phi, and the error manually set to 0. On the left side, you can see the time dimension. The purpose of this dimension is to predict the R and phi to compensate for the system processing and other delays of intrinsic nature. We know that the R and phi that are supplied to the ANN, because of the system processing time and other delays, they may correspond to a previous time. So in order to address that, we predict using LSTM networks. In fact, modified version of LSTM networks, we use peephole connections, the details of which are present in our paper. Finally, through fully connected dense layer, we get the predicted R and phi. The trick here is to have the prediction horizon equal to the system processing time for exact compensation. So this is run and updated p times to have a p ahead instance of R and phi for the purpose of compensation. So we simulated this system. We used a dual core parallel simulation where on one of the cores we had the control algorithm and on another core we had the system dynamics, so that we can match the simulation as close to the realistic conditions as possible. On the top left, you can see the inclinations. On the bottom left, you can see the desired speed, that is the speed command given by the driver, the output speed using the deep learning based self-tuning algorithm, and we compare it with the usual Ziegler-Nicholas based tuning and the particle swarm optimization tuning. As we can clearly see, the performance of our algorithm is superior to the other techniques. On the right side, you can see the adaptively changing controller parameters. So the conclusions of the or the summary of this work are that this technique is generic and can be used with any robust controller on the front end. PID was chosen due to its widespread acceptance and proven industrial applications. Dual core parallel simulations were carried out with electric vehicle system dynamics and the deep learning self-tuning algorithm implemented parallelly on two different cores, where the prediction horizon in the DLSTA algorithm was equal to the processing time of the other core. Adaptive predictive control of electric vehicles brushless DC motor was achieved. In future, we are planning to add more parameters, generate more training data from actual electric vehicles, and to have practical experimental implementation of the system. Thank you.